Hello. In this video, we're going to look at some additional related rates questions. Now, I encourage you to treat this like a problem-solving session, so go ahead and try the questions on your own first, and then watch the video to ensure that you did them correctly. If you get stuck, of course, feel free to watch the video, but try them on your own, at least give them a good attempt so you can see where you're getting stuck. Now let's look at the first question. A city is of a circular shape. The area of the city is growing at a constant rate of 2 kilometers squared per year. How fast is the radius growing when it is exactly 15 kilometers? Okay, well, we're going to draw our city, which is a circle with a radius r. Now we know the area is growing, but what are we asked for? Well, we're asked for the radius. How fast is the radius going? So what is dr dt? What's that equal to? Well, we know the area, dA dt, is equal to 2 kilometers squared per year. It's increasing, so it's positive, and we know that the radius is 15 kilometers. Now we think about it for a bit, and of course we remember our formula, area is equal to pi r squared. We don't have any substitution to do because this equation just has one variable on the right-hand side, so we're ready to do calculus. dA dt is equal to pi 2r and then dr dt. Now we're going to want to plug in everything we know. We know a 2 for the dA dt. We've got pi times 2 times 15 dr dt. So isolating for dr dt gives us 2 over 2 times pi times 15. So we can cancel out the 2's, which gives us our final answer of 1 over 15 pi. So the radius is growing at a rate of 1 over 15 pi kilometers per year. A sphere is growing in such a manner that its diameter increases at 0.4 meters per second. How fast is the volume increasing when the radius is 4 meters long? Well, again, we're going to go ahead and draw a sphere here. Now, I always like to draw a radius when I'm talking about a sphere. We can maybe try to draw it in 3D here with a bit of a dotted line. So we have our radius, and what are we looking for? Well, we want to know dV dt. And what are we given? Well, we're given that the diameter increases at a rate of 0.4. So we need a variable for diameter. If this is radius here, maybe I'm going to call the diameter maybe capital D. I don't want to use little d because that's not a good letter, but I can use capital D. So we're told that dd dt is equal to 0.4 meters per second, and we're told that the radius is 4 meters. Again, we're looking to relate volume and perhaps radius or perhaps diameter in some equation. So we know that the volume of a sphere is 4/3 pi r cubed. Now, unfortunately, if we take the derivative of this, well, we'd be taking the derivative of r, and we don't have dr dt. We've been given information about dd dt. So we have to do something here. And maybe we could take the derivative. Maybe we could. I'll show you how to do it if you don't realize that you have the wrong derivative, the wrong variable here. So let's take the derivative. dV dt equals 4 over 3 pi times 3r squared dr dt. And we could go ahead and cancel those 3's here. So this is going to simplify to dV dt equals 4 pi. Well, we know the r, so that'll be nice to plug in. We'll be able to plug that in a minute, but we don't know dr dt. And so we need to do something to find this dr dt. So that's going to be our task over on the side here. We need to determine dr dt. Well, how do we determine dr dt? There's there's really nothing given. We know that we have d dt, but I guess that means we need some new equation. And in particular, if you remember, diameter is equal to twice the radius. So we can take the derivative of this equation. d dt is equal to 2 dr dt. So 0.4 is equal to 2 dr dt. Dividing both sides by 2, we get dr dt is equal to 0.4 over 2, which is 0.2. So now we take this information and plug it on here. Now, you could have instead taken this equation here and substituted it in the original one. So you would have had an equation in terms of diameter, and then you would have gotten the derivative of diameter, and that's totally fine. But this shows you that even if you do it, maybe incorrect is the wrong word, maybe if you do it less efficiently, you can still get the answer in the end. It just sometimes requires taking a derivative over here, and then sometimes taking an additional derivative over here. So let's finish off the problem here. So dv dt is equal to 4 pi. Radius is 4. So 4 squared. dr dt is 0.2. So we get, well, decimals are a little bit ugly. They're never nice for multiplying. So 4 times 4 times 4 is 64. But 0.2, I'm going to write that as 1/5. So our final answer would be 64 pi over 5. And so we could say the volume is increasing at a rate of 64 pi over 5. And then we look back for the units, meters cubed on volume per second. The length of a rectangle is increasing at a rate of 8 centimeters per second, and its width is increasing at a rate of 3 centimeters per second. When the length is 20 centimeters and the width is 10 centimeters, how fast is the area of the rectangle increasing? So let's draw ourselves a rectangle. We'll give it labels, maybe length and width, L and W. And we're looking for area, dA dt. And we're looking for our information that we have. Length is increasing, so dL dt is equal to 8. Width is increasing, dW dt. We're going to be told that length is going to equal 20, and width is going to equal 10. All right, well, let's set up our equation. The area of a rectangle is equal to length times width. Now, this question's maybe a bit strange because they're giving us two different rates, but that's okay. We're going to go ahead and take the derivative, and we'll realize that we do need the product rule. So the derivative here is going to be dL dt times W plus L dW dt, which initially seems bad because we have extra derivatives, but it's not too bad because we're given information on both of these derivatives. We know dL dt is 8, W is 10, L is 20, and dW dt is 3. So combining all of those numbers, we have 80 plus 60, which is equal to 140. So the area is increasing at a rate of 140 centimeters squared per second. The altitude of a triangle is increasing at a rate of 2 centimeters per minute, while the area of the triangle is increasing at a rate of 3 centimeters squared per minute. At what rate is the base of the triangle changing when the altitude is 10 centimeters and the area is 100 square centimeters? Okay, we've got a triangle here. And they're telling us something about the altitude, usually called height. And they also said something about the base there, so I'll label this as B. What are we trying to find? What are we given? Well, it looks like we're trying to find the base, the rate of change of the base. So dB dt. And what do we know? Well, we know the altitude, so dH dt is 2 centimeters per minute. And, oh, we also know the area. We know dA dt is 3 centimeters squared per minute. And we know that the height is going to be 10, and the area is going to be 100. Again, think back, what's a formula for the area of a triangle? Well, it's 1/2 base times height. And again, because we have two rates here, we don't have to isolate and somehow get just one variable. We can use the product rule. It's not always advised, but in some situations, it's the only option you have. So you do dA dt equals derivative of 1/2 b is 1/2 dB dt times h plus 1/2 b dH dt. So we plug in everything we know, and, well, dA dt is 3. dB dt, we don't know that one. H is 10. B is, oh no, we don't know B, we don't know the base. We do know dH dt, so we have 1/2, but we're missing something over here. And then we know dH dt is 2. So we got to do a little work on the side. We need to determine B. Well, we could solve for B because we have this piece of information for A. If the area is equal to 1/2 base times height, well then 2A over H will be equal to the base. So the base will be equal to 2 times the area of 100 divided by the height of 10, which gives us 20. So that's our number we're looking for here. The base is 20. Let's go ahead and finish off our problem. So we're going to get 3 is equal to 10 and 1/2 will make 5 dB dt, plus 1/2 and 20 will make 10, times 2 is another 20. So we can move that over. Negative 17 is equal to 5 dB dt. And so our final answer will be dB dt is equal to negative 17 over 5. So the base is changing at a rate of negative 17 over 5 centimeters per minute. Now I used the word changing. You could have said decreasing and then put a positive number there, but sometimes you can just say changing, and the word changing doesn't mean positive or negative. So it's a way to save yourself if you're not sure exactly what's going on. And in this situation, you might be a little concerned because, well, the height is increasing, the area is increasing, why is the base not increasing too? But it's just one of those particular things where maybe the area is not increasing fast enough to keep up with that increase in height. So overall, what's actually happening is the area is growing overall, but the height is growing so fast that the base has to shrink a little bit. Otherwise, the area would grow too quickly. Now, I don't expect you to be able to conceptualize all of these in the midst of a test. As long as you work the math, you'll get the correct answer in the end. But know that sometimes you can get negative rates while other ones are positive. And that can happen sometimes on certain questions. If a snowball melts so that the surface area decreases at a rate of 1 centimeter squared per minute, find the rate at which the diameter decreases when the diameter is 10 centimeters. All right, let's draw ourselves a sphere for our snowball. And we're told something about the area. Maybe I'm going to hold off on labeling the picture just yet. We're trying to find the rate of the diameter decrease Now maybe I will label it after all. Let's maybe give this x for diameter. So we're trying to find dx dt, the change in diameter. Well, what are we given? We know the surface area. So we have dA, where A is surface area. It's going to be decreasing, so -1 centimeters squared per minute. And we know the diameter, so in this case x, will be 10 centimeters. So what's the surface area for a snowball? Surface area for a sphere? Well, if you think about it, the area formula is 4 pi r squared. And that r is just going to get in the way because we don't have a dr dt. So I'm going to try to substitute it in right away. If I know that the diameter, x, is equal to 2 times the radius, well then the radius must be equal to x over 2. So another formula that you might not have heard of before is that the area is equal to 4 pi times diameter over 2 squared. Well, we can expand that out. X squared over 4, which will just give you area is equal to pi x squared. So the surface area of a sphere is pi x squared, where x is the diameter. Kind of a neat formula. Let's go ahead and take the derivative. dA dt is equal to pi times 2x dx dt. Substitute in what we know. So we've got -1 equals pi times 2 times 10 dx dt. Isolating for dx dt gives dx dt equals -1 over 20 pi. So the diameter is, in this case, decreasing at a rate of 1 over 20 pi centimeters per minute. At noon, ship A is 150 kilometers west of ship B. Ship A is sailing 35 kilometers per hour, and ship B is sailing north at 25 kilometers per hour. How fast is the distance between the ships changing at 4 p.m.? Okay, let's take a look at this situation. It's a bit tricky to draw, but what we want to do is draw a snapshot in time. Not where they initially start, but after a little bit of time has passed. Just like you would never draw a sphere as a dot. If the balloon was blowing up and up, you wouldn't just draw it at the beginning where the balloon was completely deflated. You'd draw the balloon after some air had been put into it. In the same way, you draw the situation as though some time has passed. Ship A is going east, ship B is going north. So we're going to have ship A somewhere over here-ish. This is ship A. And then ship B is over here. Ship A, of course, we know is going this way, and ship B is going this way. Well, we want to find how fast the distance between them is changing. So I'm going to call this L for the length between them. And of course, we're going to have an X and a Y to finish off our triangle. So we want to find dL dt. That's our goal. Now, what do we know? Well, ship A is traveling east at 35 kilometers per hour. What that means is over time, X is going to get smaller and smaller and smaller, which means that dx dt is actually negative 35 kilometers per hour, because in the diagram, X is going to shrink as A moves to the right, to the east. On the other hand, dy dt, which is ship B's speed, is going to be increasing. So positive 25 kilometers per hour. Now, we also know it's going to be at 4 p.m., so this is going to be our time 4 p.m. Now, we need to think of an equation that relates L and X and Y, and I think Pythagoras is a good choice. L squared equals X squared plus Y squared. So taking a derivative, 2L dL dt equals 2X dx dt plus 2Y dy dt. Now, we need to plug in some numbers, and we have dx and we have dy, but we don't have x, y, or l, so we need to determine all of those, actually. So over here, we're going to need to do a lot of work to determine x, y, and l. To find x, we'll start with that one. We know that the ships initially, ship A was 150 kilometers west of ship B. So what that means is x started off with a separation of 150, and over time, it was less and less and less. In fact, after 4 hours, well, it would be 35 kilometers per hour times 4 hours, or 150 subtract 140, giving us 10. So the distance at 4 o'clock in terms of the x direction would be 10. Similarly, we can find the y distance. Now, there was no vertical separation to start with, so y will just be equal to the positive 25 that it's moving times 4 hours, which is 100. Then to find L, we definitely have to use this equation. L squared is equal to x squared plus y squared. So let's see what we get here. L squared is equal to 10 squared plus 100 squared, or it's equal to 100 plus 10,000. So L squared is equal to 10,100. L will then be equal to the square root of that. And we need to simplify this to hopefully cancel things later on. So if we look at 10,100, we could write that as 100 times 101, which would allow me to simplify that radical to 10 root 101. Remember, when we're simplifying a radical, we try to find the biggest perfect square that goes in this case 100, and then we take the square root of each one individually. So the square root of 100 is 10, the square root of 101 we leave as 101. So we'll plug all this information back into our question and keep going. So we have 2 times 10 root 101. dl dt, we don't know, and that's okay because we're actually trying to find dl dt. 2 times 10 dx dt is negative 35 plus 2 times 100, and then dy dt is 25. Now, we do want to simplify this eventually, and you might be noticing that there's actually a 20 in common with all these terms. We can divide each piece by 20. So we'll divide by 20, cancel that. We'll divide by 20, cancel that. If we divide by 20 over here, it'll cancel this and this, giving you 10 left over here. So a lot of cancellation, but now we have a bit of a simpler equation. We have the square root of 101 dl dt equals negative 35 plus 250. So square root 101 dl dt equals 215. dl dt equals 215 over root 101. So we need to answer in words and we're done. We can say the distance between the ships is changing at a rate of 215 over root 101 kilometers per hour. A boat is pulled into a dock by a rope attached to the bow of the boat and passing through a pulley on the dock that is 1 meter higher than the bow of the boat. If the rope is pulled in at a rate of 1 meter per second, how fast is the boat approaching the dock when it is 8 meters from the dock? So for this diagram here, we're going to have a boat. So you can draw a little boat if you want. I'm just going to draw it as a point. And we're going to have a dock that's a little bit above the boat. It says it's 1 meter. And then we've got a rope here. And then we've got here a distance, a horizontal distance. Well, I'm going to go ahead and label these as x and L. And we're looking for dx dt. We're given, of course, that dl dt, the rope is being pulled in at 1 meter per second. So it's shrinking. The length of that rope is shrinking by minus 1 meter per second. And we know that x will be equal to 8. Well, x squared plus 1 squared is equal to L squared. So 2x dx dt is equal to 2L dl dt. I can cancel the 2's, and I'm isolating for dx dt. So dx dt is equal to 2L over 2x. Cancel those 2's. dl dt. I'm going to plug in for dl. I'm going to plug in for x. I just need to plug in for L as well. So over here, we're going to determine L. So I know x squared plus 1 squared is equal to L squared. So 8 squared plus 1 is equal to L squared. So 64 plus 1 is equal to L squared. So L is equal to the square root of 65. That tells me that I have dx dt equal root 65 divided by 8 times negative 1. So the boat is approaching at a rate of root 65 over 8 meters per second. Now, just interesting to note here, the number root 65 over 8 is a little bit more than 1. So it's kind of interesting that as you pull the rope in at 1 meter per second, the boat actually comes in a little bit faster than 1 meter per second. And this is something to be aware of if you're ever going to be looking at large ships and in terms of ropes and pulleys. You have to be careful when you're pulling things because they may begin to move quicker than the speed at which you're pulling them. It's a bit counterintuitive, but the calculus bears that out. So it's an interesting situation here. Gravel is being dumped from a conveyor belt at a rate of 30 feet cubed per minute. And its coarseness is such that it forms a pile in the shape of a cone whose base diameter and height are always equal. How fast is the height of the pile increasing when the pile is 10 feet high? So here we go. Got our cone. And we know that the height and the diameter are the same. So we can give that h, and we can give that h. Don't go adding extra variables if you know they're both the same. We're looking for the change in height. And we know that the volume, because gravel is being added, it's the volume, is increasing at 30 feet cubed per minute. And we also have h equaling 10. Now we're going to go ahead and set up our formula. The volume of a cone, if you remember, is 1/3 pi r squared h. Well, we don't have r, so that's a bit silly. We should write it in terms of diameter. We know that diameter is equal to, well, 2r. So r in this case would be equal to diameter over 2. And our diameter has actually been labeled as an h, so it's h over 2. That gives us v equals 1/3 pi h over 2 squared h. So that'll give you 1/3 pi h squared over 4 times h. So volume is equal to pi over 12 h cubed. We'll go ahead and do a derivative, dv dt, pi over 12 times 3h squared dh dt. We could reduce that 3 and that 12 to give you 4. And we can start plugging in what we know. Well, we know that the height is going to be 10. We know that the dv dt, so there's nothing actually extra to determine. We get 30 equals pi over 4 times 10 squared dh dt. So dh dt is equal to 30 divided by, well, 10 squared will be 100. And then it's also going to be divided by the pi, but it's going to get multiplied by the 4. So let's try to reduce this the best we can. The 30 and the 100 will reduce to a 3 and a 10. The 4 and the 10 will reduce to a 2 and a 5. So we're going to have dh dt equals 6 over 5 pi. So we've got our answer. The height is increasing at a rate of 6 over 5 pi feet per minute. So for homework, you can go ahead and give some questions in the textbook a try. Definitely make sure you only try the odd questions here. There's no sense doing the even questions because there are no solutions for them. But do the odd questions, you have both answers and solutions. So you should be able to get a start on some of those. Thanks for watching.